Okay, we are moving on, and we're going to start looking at shapes. So tetrahedral and bent and stuff that hopefully you learned before, but maybe not. So we'll look at molecules and their shapes. So we're going to go through that, and we'll talk about things that don't follow the octet rule. But there's this one piece in the notes that I do need to change at some point, and it's really small, but it actually does show up on the test. So we need to pay attention to this bond length. Okay, so the way bond length works is that in the real world, when you have a bond, so like you have a single bond or a double bond or a triple bond, what happens is as the bonds, as you get more bonds, they're actually shorter and they're actually stronger. So our triple bond is going to be the shortest, but our triple bond, because there's three of them, is also going to be the strongest. And so what happens is that as you get more bonds, then you have a stronger bond, but you also have a shorter bond. And it should make sense that more bonds would be stronger, not necessarily that they would technically be shorter. This is a test question, and you're going to have to know this, and it just shows up in this one little tiny area. But you want to note that this is normally a test question because it's really easy, multiple choice. And so, like the triple bond is the shortest, but also the strongest, where the single bond is going to be the longest, but also the weakest, which should make sense that it's easy to break a single bond, harder to break three. So, okay, octet rule. Octet rule is that idea of that magic number of 8, which is kind of what all of our atoms are trying to do, trying to get to 8, trying to get that stable, super stable configuration. But there are a few elements that are okay with less than 8. So those have incomplete octets. So they got less than 8. And so these don't come up a lot. I do mention them, but they don't come up as that much. But beryllium can be okay with just 4. Pen got kind of messed up. With 4 valence electrons, and boron can be okay with 6. And you can see some examples over here. The boron is a little more common than the beryllium. But what's actually way more important is the structures that have what we call expanded valence shells, meaning they have more than 8. So what it says here is that when the central atom is surrounded by very electronegative atoms, and so when we talk about very electronegative, things like fluorine and oxygen and nitrogen and chlorine, these are all pretty electronegative. If you have very electronegative atoms on the outside, then you can have more than normal. And so you could have 10 or 12 valence electrons. So you could have situations where you have something in the middle and it has like 1, 2, 3, 4, 5, 6 attachments, which would be 12 electrons. And so you're going to see things that break that magic rule of 8. Okay, it's still a very good rule. It does work most of the time. It's just that, like a lot of things, we have exceptions, and this is going to be one of them. So, okay, here we go. Valence shell electron pair repulsion. Very important to know if you have a question that asks is going to ask you about, okay, why is this shape? Why is this tetrahedral? Why is this molecule linear? Why is it bent? Well, this is going to explain why. So the V stands for that's the highlighter. V stands for valence. And then S is shell. E is electron. P is pair because they show up in pairs. And then the most important word is probably the last word, which is repulsion. So, what does that mean? What does valence shell electron pair repulsion mean? Well, it means that electrons don't like each other. So you got an electron, and you put it next to another electron. Well, what are they going to do? They're going to try to spread out. They are going to repel. So why does water look like this? Why is it a bent shape? Well, it's a bent shape because the water has electrons here and here and here and here. And the bent shape is as far away as they can get from one another and still be attached in the middle. So the idea that the electrons push each other but yet are attached to a central atom means that all the shapes we're going to talk about are based upon the fact that all of the electrons are going to push away from each other, and that's why they're going to make the shapes that they make. Okay, so let's look at the terminology. Electrons in bonds, okay, so electrons in bonds, these are bonds, so that's a bond. Electrons in bonds and as lone pairs, that's a lone pair, form areas of negative charge. So this is an area of negative charge right here, and this is an area of negative charge right there. So they form areas of negative charge or electron density. Those are two words for the same thing. So electron density, a dense area of electrons or negative charge. And here it is, they repel each other. They don't like each other. They want to get away from each other. Just like a negative magnet, they repel each other. And so these electron domains determine the shape of a molecule. So what the heck is an electron domain? An electron domain is a bond, and that can be double, single, or triple, or lone pair, because both of these are going to have a negative charge. So it can be a bond, so like a single, a double, or a triple, or it can be a lone pair. So if I look at water here, it has 1, 2, 3, 4 areas that are either bonds or lone pairs. So it actually would have 4 electron domains. So what you can say, if they said, hey, why is water bent? Well, you can say, okay, water's bent because it has 4 electron domains that repel each other. That's the why. So you have to get that concept of repel in if you are ever asked, if they ask you a question about why. So why is this shape this? You can't say why. You can't answer a why question without talking about the electrons repelling each other, talking about these electron domains. So this comes up a lot of times as a test question, and it's normally a why that you're answering. So the why, you want to talk something about those electron domains. So, okay, let's get to the shapes. So here are the shapes. So I need to talk to you guys a little bit about the A's and the X's. Okay, so I need to talk to you guys a little bit about the A's and the X's and what the heck those mean. So first of all, when we talk about this stuff, the A's and X's are going to be a thing to help you remember the shapes. The A's and X's are not something you would write down as an answer. They're a way to help you memorize the shapes. So what are the A's and the X's and the E's? Okay, so the A is going to be a central atom. So most everything is going to have a central atom. And so if it follows our patterns, it's going to have a central atom. Okay, so we're not going to deal with a lot of things that don't have central atoms, and so that's going to be super duper common. Okay, what is an X? An X is anything, an X is attached. It's going to be, actually I probably should write down, this is going to be an element attached to the central atom. Okay, so you got your A. Everything's going to have an A, central atom. You can have multiple X's, right? So you could have multiple things attached to the middle. And then what the heck are the E's? An E is a lone pair. So an E is a lone pair. So like that would be an E, right? So we represent the lone pair with the E abbreviation, okay? Now, once again, this is a way for you to memorize the shapes, and there's a whole bunch of them. Sadly, you're going to have to memorize them. So how does this work? We draw a dot structure. Based upon the dot structure, we're going to attach A's, X's, and E's, and then that's going to take us to the correct shape. Now over here on my table, the ED, that is going to be the electron domains, and you're going to see that there's going to be some overlap there, but that's the